So we've been talking about linear transformations and about the fact that there's tons of numbers floating around. And when you have just an arbitrary matrix representing some linear transformation, it's not really clear what its key features are. And we want some way of distilling a linear transformation into sort of a normal form that makes the geometry of the transformation more clear, right? And so, as an example, let's go ahead and consider this transformation here. Suppose we have minus 43, minus 16, 120, and 45. This is sort of what we're talking about here. We've got just a seemingly random collection of numbers, but if you change basis, so this is expressed in terms of some basis, and if you change basis, which we haven't really talked about yet, we're going to get to that probably next lecture, then you can rewrite this transformation in a much cleaner form. This thing turns out to be equivalent to this transformation, where the only difference is we're using a different basis to express the linear transformation. So clearly, we have a lot of options in terms of this distilling process. And so today we're going to talk about eigenvalues and eigenvectors that are really important in this process of rewriting things. There's lots of different ways of rewriting it. There's, this matrix turns out to be diagonal, which is sort of the nicest possible case. There's another form called the rational canonical form that this is actually in rational canonical form right now. It's also in Jordan normal form. And then there's something called singular value decomposition. So there's all kinds of different ways you can rewrite matrices to put them in nicer forms. And I keep talking about the Jordan normal form, which is where we're headed, right? And so, yeah, this thing is actually in Jordan normal form. And it's also in rational canonical form. Anyway, so eigenvalues and eigenvectors are really key in the study of the Jordan normal form. So let's go ahead and take a look at a simple transformation where let's go ahead and consider 3, 2, 3, negative 2. And this transformation, I'm just going to do sort of a rabbit out of a hat method of pulling out an important vector. Let's consider this vector 2, 1. Then this vector and this matrix are closely related in the sense that if you consider A times that vector, we get 3, 2, 3, negative 2 times this vector 2, 1. And so just multiplying these things, regular matrix multiplication, we'd end up getting 6 plus 2, which is 9. And, which is 8, I guess. 6 plus 2 is 8. And then this row times this column gives us 6 minus 2, which is 4. I think I got that one right. And each of these has a factor of 4, so this can clearly be rewritten as 4 times 2, 1. And so we notice that we have this special relationship between this matrix and this vector, which you just hit that vector with this matrix, and we end up getting a rescaled version of the original vector, right? And so this is what's called an eigenvector. And eigenvector for a given matrix is one in which if you hit that vector with this matrix A, it ends up sending V to a rescaled version of itself. And we assume that all eigenvectors are non-zero. So 0 is excluded from being an eigenvector. Because it doesn't really have the features that we look for in an eigenvector, right? It's sort of it certainly satisfies this, but it doesn't have the sort of important features that we care about when we want to think in terms, when we want to think of an eigenvector. So okay, so I guess we could say a non-zero vector. V is called an eigenvector for A. It satisfies that relation. Okay. This coefficient here, lambda, is what's called the eigenvalue associated to eigenvector V. And so that's all well and good. We've got these nice definitions here. But just writing some definitions on the board certainly doesn't give you any sense of how you actually find eigenvalues and eigenvectors. So, I should point out that this matrix here, A, I actually stole this from, I just feel like I should say this since this video is going on YouTube eventually. I actually stole this from, Patrick JMT. I stole this from him. I was like, what's a good matrix to use for eigenvector demonstration? So I went and found Patrick JMT's matrix, and so just a little YouTube shout out. Anyway, so how do we actually find these things? And what we'll do is, first of all, we know this condition, AV equal to lambda V. If that condition is satisfied, then we can rearrange this equation as, and I'm actually going to write it the other way around. We'll take lambda V minus AV equal to 0. And we can certainly think of, in this term here, we can certainly think of there being an imaginary identity matrix sitting right here. Or not even imaginary. It's real. And after we rewrite it in that way, now we can factor out that V in a sensible way. We notice that factoring out this V we get this matrix equation here. And what you'll notice is that this is certainly, V is certainly a non-zero vector. And what you'll notice is that this transformation then has, we haven't really defined this term properly, but it has a non-zero kernel, right? We notice that this transformation here sends a non-zero vector V to 0, and so it has a non-zero kernel, which means that this thing is a singular matrix, right? So since lambda I minus A has a non-zero kernel, the transformation lambda I minus A is singular. And the reason that's important is because what's the determinant of a singular matrix?
some non-zero value?
It's 0.
That is 0.
Yeah, determinant of a singular matrix is 0. And so what that gives us is it gives us a polynomial that we can then solve for lambda. Okay, so this is going to give us a polynomial equation. In variable lambda. And in solving for lambda, that'll give us eigenvalues. So without further ado, let's actually work through this. We've got a 2 by 2 matrix, so we'll have 2 by 2 identity, right? And we've got lambda times 1, 0, 0, 1, minus the matrix A, 3, 2, 3, minus 2. Okay. This can be rewritten as determinant of this matrix here, lambda minus 3, 0 minus negative 2, 0 minus 3, and lambda plus 2. From here, we know determinants, just multiply down the diagonal and subtract along the second diagonal. So that product here, lambda minus 3, lambda plus 2, going down that diagonal, and then go up this diagonal and subtract that product. So we'd have a minus 6 at the end. And then just some algebra here. We get lambda squared minus lambda minus 12. Okay, and we're assuming this is equal to 0 because we're assuming V is going to be an eigenvector, and that it's going to satisfy that singular. You know, that makes this thing singular, right? So once we have this, we can just, you know, in this case it factors pretty nicely as lambda minus 4, lambda plus 3. And there we go, we've got lambda equal to 4, lambda equal to negative 3. And these are going to be the eigenvalues for our transformation. So any questions on what we've done so far? And now, what we'll do is we'll say, let's go ahead and let V be an eigenvector with one of these eigenvalues. Okay, so let's let V be an eigenvector with eigenvalue 4. Then the algebraic condition that it satisfies is the matrix A, 3, 2, 3, negative 2, times this eigenvector has to equal 4 times the original. And this is, you know, at this point, really just a system of equations, right? We can rewrite this in system form. We notice that we get 3x plus 2y equal to 4x, and 3x minus 2y equal to 4y. And then we can rearrange this thing. We notice that we get minus x, or I guess we can write it, I'm just going to skip some steps here. We get x equal to 2y, and we get x yeah, 3x equal to 6y. Okay. And so these two equations, they turn out to be the same, right? It's just the same equation, slightly rewritten. And so, in other words, there's going to be infinitely many solutions to this equation, right? So all that we have to do, we just pick one, right? And so, in this case, let's go ahead and just set y equal to 1. And we're just going to pick any solution to this equation. If y is equal to 1, then we see x is equal to 2. Nice work. And that gives us an eigenvector. We notice that our eigenvector b is going to be 2, 1. And we have choices here, right? We can have, we can have different eigenvectors because any vector in the span, so this is an eigenvector 2, 1, right? And any rescaling of that eigenvector is also going to be an eigenvector. And you can just pick any one of those to be an eigenvector. And so, there we go. We've got perfectly good eigenvector 2, 1 associated with this eigenvalue, lambda equal to 4, right? Okay. We'll go ahead and run through the next one as well and find an eigenvector associated to lambda equal to -3. So AB equal to lambda b means that 3, 2, 3, -2 times xy has to equal -3 xy. And this system becomes so that matrix equation looks like this after rewriting in system notation. And so adding 3x to both sides and subtracting 2y from both sides, this equation becomes 6x equal to -2y. And this equation would become 6x no, sorry. 3x equal to -y. So again, these are the exact same equation, and we again just pick a solution. And so in this case, I think choosing x equal to 1 would be a good choice. And in that case, plugging that into one of those equations there, you find that y has to be -3. And so our second eigenvector then is 1, -3. All right, good. So now that we have this set of eigenvalues and eigenvectors, the underlying geometry of the space is going to be a lot more clear. The underlying geometry of the transformation, rather. And so I thought we'd just run through a quick little matrix calculation and then pair it up with the geometric picture that is going on behind the scenes. Okay? And so let's go and consider this matrix A. Acting on this vector. Three, -2. Then we can certainly, just compute this thing, and it's not difficult, it's just multiplication, right? 3, 2, 3, -2. On this vector 3, -2, you just, matrix multiplication says you get 9 minus 4, which is 5, and 9 plus 4, which is 13. So what have we got? We've got this vector here, 3, -2. Gets sent to 5, 13. Nothing wrong with that, but, the exact relation, exact geometric relation between this original input vector compared to that output vector is not necessarily that clear. And so what we can do is think in terms of these eigenvalues and eigenvectors for a moment. And so what we'll do is, instead of thinking of A in terms of the regular basis that says A is 3 units this way and 2 units down that way, let's go ahead and re-express it in terms of these eigenvectors. Okay? And we'll talk about how you do that a little bit later on. And for now, let's go and just, again, sort of the rabbit out of the hat method of our vector 3, -2 can be thought of as a sum of the first eigenvector 2, 1 plus the second eigenvector 1, -3. And so, let's call this V1, V2. Then, to determine how A operates on A, on lowercase a, really we can just take A times V1 plus V2, which, these things are eigenvectors, and so the operation turns out to be really clean. A times V1 just gives us 4 V1. A times V2 gives us -3 V2. And then we can just deposit the eigenvectors in here and perform the calculation. So we've got 4 times V1 is 4 times 2, 1. And -3 times V2 is -3 times, what did we say, 1, -3? And so, this is just arithmetic from here on out. You get 8 minus 3, which is 5, and 4 plus 9, which is 13. So, no surprises, we end up getting the same output vector. But now, the underlying geometry of the scenario is a little bit more clear, right? We've got this original vector that had coordinates 3, -2. What we did is we first re-expressed it using the eigenvectors, right? And we said, here's our V1. V1 was 2, 1. And here's our V2, which said 1, -3. And so if you use parallelogram law with these two vectors, we were able to generate A as a sum of V1 and V2. The transformation then said, well, A on V1 is just going to rescale it by a factor of 4. So we have this thing with A, and we get 4 V1. Acting on V2, we know that A on V2 is going to give you -3 times the original, so it's going to shoot this thing backwards and rescale by a factor of -3. So -3 V1, sorry, V2 rather. And from here, it's absolutely clear why this thing took this original input vector and shot it way back over here. It's because it's the sum of that many units in the V2 direction and this many units in the V1 direction. And as simple as that, you just form the resulting vector out of the parallelogram law. And so, what originally appears to be just a jumble of numbers really has this pretty simple geometric interpretation that we see here. So that's actually it. It went a lot faster than I expected, and I don't have any additional notes prepared, which actually we only got 10 minutes left anyway, so it is for the better.